So in this chapter, we do about heat engines. Heat engine would be a gasoline engine, would be a good heat engine. A steam engine would be a good heat engine. Basically, if I take gasoline and I ignite it, the energy as heat goes to the cold environment. So I get this, I get the hot goes to the cold. And that's what happens. If I'm really clever and I make myself some kind of internal combustion engine, what it does is it kidnaps some of the heat and it changes it into useful work. Now, frankly, all heat engines work to overcome friction, air resistance on your car, friction in the engine. And so all that work goes to heat. So it goes into the cold. So in the end, we're not really changing much. We're just grabbing some of that energy on its way to the cold sink and having it do useful work for us. The car doesn't care whether it's at the shops or at your apartment. It doesn't care. All it knows is that rather than just burning the gasoline, you burned the gasoline and turned some of that energy into mechanical energy, but it turned that mechanical energy into heat. So it's just like, oh, okay, I did something. This diagram is incredibly useful. If I tell you how much energy comes from the hot source, and I tell you how much energy went into the cold sink, you can tell me how much energy was left over. That's that equation, if you like. The energy, the heat coming out of the hot is equal to the heat going into the cold plus the work done. Simple as that. The efficiency of an internal combustion engine, well, that's just what you get out, which is the work, over what you put in, which is the energy from the hot. Don't care about coefficient of performance. Don't worry about it. In a heat engine, (100 joules of heat is taken from the hot reservoir. 60 joules of heat is dumped into the cold reservoir. How much work is done? Q hot is equal to Q cold plus W. 100 equals 60 plus W. W is equal to 40 joules. Simple as that. Simple as that. Let's on this question, let's also do the next bit. What's the efficiency? Efficiency is equal to what you get out over what you put in, which equals 40 over 100, which equals 0.4. And if I want, I can express that 0.4 is equal to 40 over 100, which equals 40%. So don't get confused about saying it's 0.4%. How efficient is a typical automobile? 30%. 2/3 of your gasoline is just completely wasted. How efficient is a power station like at Big Bend? About 30%. 2/3 of your fuel is wasted. Maybe 40 on a good day. How efficient is a nuclear power station like we used to have at Crystal River before they broke it? How efficient? Less efficient than a coal-fired power station. Less efficient from a gas-fired power station. Because of the radiation problem, they have to use a heat loop. You don't want the radioactive water to go into your turbine because you have to maintain your turbine. So you have a heat exchanger between the radioactive side and the non-radioactive side, and that heat exchanger is not 100% efficient, so you lose efficiency. So these are just examples Don't worry about coefficient of performance. The other two, one's doing, don't worry about the coefficient of performance. Know how to get the efficiency, know how to get the one that's missing. Internal combustion engine. I would like you to know the order of the strokes, and I'd like you to be able to tell me what the configuration of the cylinder is. So let's go through that. This wheel down here is spinning, and sometimes it's pushed by the piston and sometimes it is being pulled by the piston. The way it starts is the piston has been pulled down, you open up your intake valve and you draw in your fuel-air mixture. That's the first stroke. It's called the intake stroke because you're taking in the fuel-air mixture. Then you have the upwards motion of the piston. The wheel goes round and eventually it starts pushing the rod back up. So you get the upwards motion of the piston. And when that happens, you close your intake valve and you just let the air-fuel mixture compress. Don't do this, but if you've ever seen anybody take the gunpowder out of a firework and light it, it's not as impressive as if they leave it in the cardboard casing and let it thing go bang. The reason why you get that explosion is because the cardboard keeps it compressed until it can overcome. It's the same kind of idea with this. Compress it and then ignite it. Don't ignite it before. And so we get this. Pardon?
What's the SP?
Spark plug. So when this thing gets to the top, you ignite your spark plug and burn the gas. You heat the gas up. Rapid expansion. Piston goes down. That's the power stroke. And then we have the exhaust stroke. You open up the piston's naturally on its way up. You open up the exhaust valve. You let the burnt fuel come out. Fuel is not completely burnt in a typical engine. There's usually some residual fuel that's not been burnt. Why don't we burn all of it? Because it takes time to burn all of it, and that increases efficiency but reduces power. And we want power. We might say we want efficiency, but we want power. A little Honda 50 is really efficient. It's just not very powerful. So we want power. We want a nippy car. And the European way of making a nippy car was you made a really small, light sports car. And because gasoline was expensive. And the American way of making a sports car was you took a normal car and put a huge engine inside it. One of my brother-in-law had a muscle car, and he told me he got 8 miles to the gallon. And a car, not a truck, a car, 8 miles to the gallon. I'd like you to know the order of these. I'd like you to know when the valves are open, when the valves are closed. This is, this is recognizing what we're doing on a PV diagram. When you open up your intake and you draw pressure, air pressure gas in, you're doing that. What kind of change is that? It's isobaric, isn't it? Constant pressure. When I squish a gas really quickly, is it an isothermal change or is it an adiabatic change? Is the temperature staying the same? No. Am I allowing heat in or out? No. It's so quick. So there's your compression stroke, and that is an adiabatic change. I then light my spark plug and I get immediately a constant volume increase in temperature. That's the thing lighting, which causes an increase in pressure. And then I get an adiabatic expansion. So my power stroke is from C through D to E. And then I open up my exhaust valve. The pressure falls and I push the gas out. So, intake is A to B. Compression is B to C. Power is C to D to E. Exhaust is E to B to A. I'd like you to know that. I'd like you to know which is isothermal, there aren't any, which is adiabatic, which is constant volume, which is constant pressure. Don't worry about this. This is the theoretical best you can do. It's a Carnot cycle. Don't worry about it. That's what it means. Don't worry about it. Okay. What is the name for the stroke in which the intake valve is closed and the exhaust valve is open? Yeah, it kind of goes like that, doesn't it? What's the name for the stroke where the intake valve is open and the exhaust valve is closed? The intake. Yeah. The other two, they're both closed. What is the name for the stroke in which the intake valve is closed, the exhaust valve is closed, and the piston is moving downwards? Power. It's pretty straightforward. This is easy, low-hanging fruit. And then along came somebody who said, you know, if I could get my internal combustion engine to work backwards, I could cool things. I could shove energy from the cold bit to the hot bit. Well, it don't work like an internal engine. It works like a refrigerator. And a refrigerator works by storing energy when you vaporize and giving up the energy when you liquefy. And the trick is, I don't have to do that in the same place. If I can vaporize a liquid in my house and then take that vapor outside and condense that liquid in the backyard, I take in heat in my house and then I expel heat in my backyard. I'm using a mechanical change to drive a thermodynamic change. And so, you don't need to worry about that. You don't need to worry about that. All you need to worry about is this. So, if you have a constriction, you have a pump, and a tube. If you want cooling, cause vaporization. You want to cool inside your house, vaporize inside your house. How do you vaporize? You reduce the pressure. So low pressure in this pipe means vaporization, means cooling. High pressure in this pipe means condensation, means heating. I want you to know that. When heat pump is in the air conditioning mode, where is the liquid vaporized? You want to cool inside the house. So where do you vaporize? You want to cool inside your house. Lick your finger. This is the last thing you're going to do in my class, so do it. Keep this one dry, this one wet. Blow on both of them. Which one got colder? The liquid. Why? Your breath's your breath. You're blowing away the vapor. So it says, I'm going to create more vapor. You're blowing away the vapor. It takes more vapor. Mechanically, you're causing a thermodynamic change. So you want cooling. Who's been to Arizona and been swimming and got out of the swimming pool and nearly died shivering? Because you vaporized. All the water just comes off you straight away. Notice after it rains, it cools because of vaporizing. So when a heat pump is in the air conditioning mode, cooling the house, where you are vaporizing inside in the house. And then if the refrigerator is left on with its door open in a well-insulated room, this is where we're going to end. We've got no more after this. Oh, entropy, just know the name exists. If I leave a refrigerator with its door open, it's cooling the inside of the refrigerator, but it's heating up the back of the refrigerator. Yeah. So if it's a 100% efficient refrigerator, I have no change to the room. Because what I cool, I give back.
No change in temperature.
But if it's not 100% efficient, I heat up the room because I give out more than I take in. Entropy is just like disorder. That's all I know about it. Yes?
Which sections are we going to have in the next test?
My notes say it's everything from gravity, including gravity onwards. Am I right?
Yeah.
Gravity onwards.
And then the final, everything till gravity.
Finally is everything that was on the first three tests. Yeah. So everything until gravity.
Well, everything on the first three tests. So gravity is not included.
Which three tests? Finally. Gravity will be.
Oh.
Yeah. Because I don't have time to feed you back. And you did well on that. So, lab. If you have not missed a single lab, you can miss this lab. But I could have your lab book,
And the formal lab.
and the formal lab. So come along to lab for a minute, and we'll just sort it out, and you can leave. Don't ask me today. Don't ask me.
Sir,
I hope you can when you're listening. Oh, I didn't hear that.
so what's the connection relationship between the T and the particle speed?
Well, where's the equation? Go back to your numbers. There's T, there's B. What's that relationship? Keep everything else constant.
I don't know.
Well, so you're not changing the 2, and you're not changing the 3, and you're not changing the KB, and you're not changing the A. So T is equal to a constant times V squared. What relationship is that?
I don't know.
You don't know
No.
linear, quadratic, inverse?
No.
Well, you need to know that because you've been doing it all semester and it's in your math. How do you recognize an inverse relationship?
I don't know.
You need to think about it. I'll gladly answer that. I want you to think about it first because you know how to do that. You know how to do that.
Since I think this is that going to be a drop?
So, what been?
I took all the other ones, but this is the last quiz. So
I need to. So let me look because
this one I guess is just going to be a 0, right?
let me double check. Are you going to the lab?
Yeah.
Let me have a look and I'll see. Okay. Chances are yes, but let me see. I'll talk to you.
What happened here with the negative? Wait. No, this one here, sorry. It's the potential here was negative 43.7, the question we did in class. And then we got negative 12.2 joules.
I might probably ask you for the magnitude.
Okay.
Just double checking and ask you for the magnitude.
Okay.
For the magnitude, okay, right sign.
Okay. But if you don't say magnitude, it can be negative, right? Can we have negative? That's gravitational potential at a
Oh yeah, if you go up, it's one way. If you go down, it's another way.
I was just wondering, is the final going to be similar to the types of problems we got on the first 3 exams?
Yes.
So the first 3 exams would be good to study.
Good
like
study,
me.
yes.
I wasn't able to get my last 2. Is there any chance of it?
I didn't get my last one out.
So names.
Adam, Trina?
That's hardly anybody got their last 2. So Alex, that's there you go.
And the one before that. I was like,
That one might be. I don't keep them forever. Let's have a look. But you got test 1?
yeah, I have test 1. This was test 1.
Wait. There you
Yeah.
go.
Thank you.
Also, yeah, I was going through this last one for O, and I would get this answer like this: 5.83 times 10 to the 10 or something like that, and then you would put it like this. It comes out to be the same thing.
Yeah.
That's an acceptable answer?
Of course.
And then for M,
But it's good. It needs units on it though.
yeah, the units are missing. I'm sorry, but the M also. When I was going back, I'm looking through all like this stuff. I don't think the homework for M matches up with the M notes. I think the homework for M matches up with L.
Thanks.
But
Okay,
the one for
that's
L,
good.
I'm sorry. Yeah, I just wanted to make sure
Yeah,
'cause I
thanks.
couldn't find it. And then
Okay.
that's it.
Okay, cool.
Yeah.
But you did do the homework.
For M,
You
not
did-
yet because it doesn't. That's not the one that's on there.
When you say the homework doesn't match up, what do you mean?
Like the one for L, I think is under M, and the one for M, I'm not sure, but it
You
just.
talk about questions or solutions?
I'm talking about the actual questions with where you have to fill in everything. I think that one for M that you have is for L, and I feel like that one for L, it doesn't go with M, because
So
some
what
of
have
it
you
like
not?
this
What have you not got homework on?
M, yeah, because L.
I don't know, I haven't
Like,
looked at it.
because L was like the same diagrams from that, like those notes were on that homework, but that one was under M.
So, let's go. So, go here. And this is, I want my HCC. Log in. Come on. Oh, you're joking.
You have to put that in Hotmail for you to send.
Either that
Oh,
or
it's
I
not
think
that.
EDU.
I'm not.
Hotmail.hccfl.edu.
EDU. That's the one.
You gotta put it
At Hotmail.
I'm not Hotmail.
Oh.
Yeah, you guys are Hotmail. I'm the guy. So we're talking about 48.
Yeah, and it's M. I think it goes with L. I think.
M, A, B, C, D, E, F, G, H, I, J, K, L, M. So you're saying that this
Yeah, that one.
homework,
That one, yeah, that homework.
angular momentum. So that bit's in a different bit,
But the rest of it is
yeah,
with M.
yeah, I think so.
Oh, my bad. I'm sorry. I just looked at the first page and I was really confused. I was like, oh, this goes with L. I think this is wrong.
No,
I'm
it
sorry.
got moved. You just
I didn't
got
mean to
moved.
waste your time
Ignore
like
that
that.
first
No, it's
question.
okay.
Yeah, my
You just
bad.
got moved.
Just ignore that first
No,
question.
no, do it because it's you know it's part of.
Oh,
It's
it's
just
part
on a
of-
different chapter.
Oh, okay.
You know. I mean, it's just. I moved it to fit it in, and it got in a different
Okay.
chapter. So I got people still waiting. I got to go to the lab. So,
I'm just returning stuff from that.
okay, and I'll bring it to the lab for me, just because then I'll sort it out. I can't carry everything. Yeah, you done? You're done. Well, you're gonna have to see me in office hours then, because I got to do lab. Yeah,
I was gonna ask you for the test back.
Yeah, me too.
test back. Okay, so what's your name?
Mine was
Which test is it?
3.
3. Okay. Augustus, that's for you. And you,
Darius, D-A-R-I-U.
oh, Darius.
Yeah, yeah.
Oh, yeah.
Yeah, it was really bad. Don't.
It's all right. I think they're going in. I need to give these back out. Darius, there you go.
Yeah.
Oh, Darius.
Yeah, I'm working on it.
Good.
This question here.
Yeah. You're gonna have to. I gotta get to lab.
Okay.
Okay.
Should I just ask you in lab or?
Yeah, you can ask me. Well, end at lab, whatever. But, yeah.